Welcome to this basic video about artificial neural networks. A neural network consists of input nodes, a hidden layer, and output nodes. For example, these input nodes may represent three measurements that we do to determine if someone has prostate cancer or not. Suppose that a person enters the hospital. We check the age and the concentration of the prostate-specific antigen from a blood sample, and collect a score between 1 and 5 from an MRI scan of the prostate. Then we plug in the corresponding values in the input nodes, and use the network to tell if the person has prostate cancer or not. To understand how neural nets work, we will here have a look at a super simple example. At the end of this video, we will try to understand what happens if we include a hidden layer, and look at some simple R code if we like to reproduce the first example shown in this video. We will here see how to train a neural network to predict if someone has prostate cancer based on the PSA level. Our training data consists of 7 patients that we know have prostate cancer, and 7 individuals that we know are healthy. Based on a blood sample, we have determined the concentration of PSA, or the prostate-specific antigen, in the blood of these individuals. Note that this data has been simulated for the purpose of this video. We'll here use the simplest possible neural network model. Since we only have one measured variable, the PSA concentration, the network will only have just one input node. Note that we here do not have any hidden layer, because we like to use the simplest possible network. The network has 2 output nodes, because we here like to use the network to predict if someone has prostate cancer or not. This is called a bias, which is used to modify the activation function. There are several different activation functions to select between. We will here use the sigmoid function, which is the same function that is used in logistic regression. This will later allow us to compare the neural network with logistic regression. Let's make a plot of this data, like this, where these points represent the cancer patients that are here coded as 1s, whereas these points represents the healthy individuals that are coded as 0s. For example, this healthy individual has a PSA level of 2.5, whereas this cancer patient has a PSA level of 2.1. Training a neural network means that we find the optimal values of the weights and the weight associated with the bias, so that the activation function in this case generates a sigmoid curve that can be used to predict the outcome in an optimal way. Note that the logistic activation function generates a value between 0 and 1, and that E is the Euler's number. If we train this simple network, we will obtain the following weights. Let's use this network to see if this healthy person is correctly predicted as being healthy by the network. We plug in its PSA level of 2.0 in the input node. To calculate the probability that the person has cancer, we use the weights associated with the output node in this equation, where W0 is the bias weight, and this is the weight for the input signal, whereas this is the value of the input node. Since we only have one weight that is associated with the output node, N is here equal to 1. Let's plug in the weights in the equation and the value of the input node, and do the math. We now plug in this value in the logistic activation function and calculate. This value is the value for the output node cancer, which can in this case be seen as the probability that the person has prostate cancer. Let's place this value here. We'll now calculate the value of this output node, where we plug in the corresponding values in the equation and do the math. Let's place the corresponding value here, which can be seen as the probability that the person is healthy. We can now use some kind of threshold to determine if we should classify the individual to have prostate cancer or not based on these two values. A common cutoff value to use in binary classification is 0.5, because it is the value between 0 and 1. Based on this cutoff value, the network will predict that the person with a PSA level of 2 is healthy, because the output value associated with the healthy class is greater than 0.5. Note that this value is exactly the same value as if we would draw a vertical line from 2 to the logistic curve, and then a horizontal line from the curve to the y-axis. The height of the activation function is therefore equal to 0.438. This value is then simply just 1 minus 0.438. This value is equal to the height of the flipped curve, because the slope of the curve should be negative if you go this way in the network. If you have seen my previous videos about logistic regression, you will note that such a model will produce the exact same results. The estimated parameters of the logistic regression model are identical to the weights in this simple neural network. B0, or the intercept, corresponds to the bias, whereas B1 corresponds to the weight associated with the output node for prostate cancer. If we plug in this equation into the activation function, we will obtain the exact same function that is used in logistic regression. We can therefore conclude that this simple neural network using the logistic activation function is identical to logistic regression. Let's see how well this neural network can predict the class of our training data. This is the data that we used to train the network, and this is the values generated by the output node for cancer, which can be obtained if you plug in these values in the equation and the weights, and then compute the corresponding values by the activation function. For example, this is the value that we calculated by hand previously based on the PSA level of 2.0, which corresponds to the height of the activation function. We can now use the output values and the cutoff value 0.5 to see how well the model predicts the training data. Since these individuals had values greater than 0.5, they are predicted to have prostate cancer. Since we know that these individuals actually have prostate cancer, we know that the neural network has made the correct predictions for these individuals. However, the network incorrectly predicts that this cancer patient is healthy. These individuals have output values that are less than 0.5, which means that they are predicted to be healthy. Since we know that these individuals are healthy, we know that they have been correctly classified by the network. This healthy person is incorrectly classified as having prostate cancer because it has a relatively high PSA level. In total, the network makes 12 correct predictions out of 14 possible, which gives an accuracy of about 86%. However, to get a fair estimate of how well the network would perform on new data, we should use a test dataset or cross-validation, as we have done in all other machine learning methods that we have discussed so far. Watch the video about validation to see how to evaluate the classifier by the holdout method or by cross-validation. Once we have established a neural network that has been trained on some data, we can use it for prediction. Suppose that we like to test if this person has prostate cancer or not. From a blood sample, we measure the PSA concentration to 1.75 nanograms per ml. We plug in the value in the network. We can then compute the values of the output nodes. We therefore plug in the value of the input node here, the weight of the bias, and this weight here, and do the math. Then we plug in this value in the activation function, and do the math again. 1 minus 0.281 is 0.719. Since this value is larger than the cutoff value of 0.5, the network predicts that the person is healthy. We'll now try to understand where the values for the weights come from. In this example, these are the optimal values for the weights, whereas these are the optimal values for the bias weights. The weights are optimized by using some sort of cost function, usually the maximum likelihood method for binary classification that we have covered in the videos about logistic regression. The following weights were optimized by the negative log likelihood function. We can also use the method of ordinary least squares. I will here explain the concept of ordinary least squares because it is a bit simpler to understand. In the videos about logistic regression, I show how to calculate the log likelihood. And in another video, I show the difference between ordinary least squares and the maximum likelihood method based on a simple linear model. When we use the method of least squares, we try to minimize this function that computes the sum of the squared errors. These are the y values of the observations, which are, in this example, equal to 0 if it is a healthy person, and 1 if it is a patient with prostate cancer. Y hat is the value of the activation function that can go between 0 and 1. This difference is called a residual, or an error, which can be seen as the distance between the observations and the curve. The y value of this data point is 0, and the value of the curve when the PSA level is equal to 2.5 is 0.75, which can be calculated like this based on the weights we previously estimated. This results in a residual of negative 0.75. We then square this residual. We then do the same calculations for the next data point and so forth. Then we sum all the square residuals, which here results in a value of 1.78. Suppose that we now change the value of the bias from negative 5.754 to negative 8. That will move the curve a bit to the right, which will increase the sum of squared errors, because the data points are now much further away from the curve. Let's place a point here, which represents that the sum of squared residuals, or errors, is 2.88 when the bias is set to negative 8. When the bias is set to negative 5.754, the sum of the squared errors was equal to 1.78. If we set the bias to negative 3, we'll move the curve a bit to the left, which will result in that the sum of the squared errors is equal to 3.62. If we would try many different values of the bias weight, we will be able to generate a curve that shows how the sum of the squared errors changes when we change the value of the weight associated with the bias. The method of least squares finds the value of the weight that results in the lowest possible sum of squared errors. This explains why the weight of the bias is equal to about negative 5.8 in this example, because that value results in a curve that is as close as possible to the data points, which will result in that the network predicts the prostate cancer in the best way. To find the value of the weight that results in the lowest sum of squared errors, we need to start with an initial guess. Suppose that we initially guess the value of the weight to negative 3. Then we use an algorithm such as the gradient descent, where we stepwise move along the direction of the steepest descent, like this. If we instead initially guess the value of the bias to negative 9, the gradient descent method will instead increase the value of the weight until it finds the value that minimizes the sum of the squared errors. One problem occurs when we have a more complicated network, because the error function for such a network will then have several local minima. This means that if we initially guess the value of the bias to -9, the method will move down to the local minimum and report -8 as the best value, which will result in a bad fit to the data. If we initially guess the value to -6.5 or -3.5, then we will reach the global minimum, which results in the best fit. It is therefore important that we try many initial guesses of the weights during the learning process to find a network that can predict the data in the best way. Most software tools generate random initial guesses of the weights, which means that you might get different results every time you train your network. We can make a similar error curve if we change this weight. When we change this weight, the curve will change its slope. When we estimate two weights simultaneously, the error function will correspond to a surface in a three-dimensional plot like this. The combined values of the two weights that result in the minimum value of this function will result in the best fit to the data. We'll now try to understand the purpose of using a hidden layer in neural networks. To show the beauty of the hidden layers, suppose that we have the following data, where one has measured a certain protein in blood samples from 10 cancer patients and 5 healthy individuals. People who are healthy have an intermediate level of this protein in their blood, whereas people with prostate cancer either have a low level or a high level. If we would try to fit a logistic regression model or train a neural network with a logistic activation function without a hidden layer, they will fail to make a good prediction of the training data because an S-shaped curve is simply not useful for this type of data. These cancer patients will incorrectly be predicted to be healthy by the model. And if we flip the curve, these patients will instead incorrectly be predicted to be healthy. The curve might also look like this, where all the healthy individuals will now be incorrectly predicted to have prostate cancer. What we want is a curve that looks like this. This is where the hidden layer comes in, because a neural network with one or several hidden layers can generate cool curves like this. We will here extend our previous network with one hidden layer. If we train this network on the following data, we'll obtain the following values of the weights. Note, if you try to compute a neural network on the same data, you will end up with different values compared to the one shown here, because you will probably end up on a different local minimum. To understand the calculations behind this neural network, let's see how it predicts a person with a value of 3 of protein X. The value of this node can be calculated like this, which results in a value that is approximately equal to 1. Let's set the value of this node to 1. The corresponding value of this node is 0.869. The value of this output node is calculated based on the bias and the sum of the weight multiplied by the first node in the hidden layer and the weight multiplied by the second node in the hidden layer, which results in a value that is approximately equal to 1. Similarly, the value of the second output node is approximately equal to 0. If the value of the input node is 3, the network will predict that the person has prostate cancer. Let's focus on how this output node is calculated. This is how this node was calculated. And this is how the values of the nodes in a hidden layer were calculated. Let's substitute x1 and x2 in the equation, like this. Then we plug in this equation in the activation function here, so that we have the following function that can compute the value of the output node based on any input value. Let's move the function up here. If we now calculate the value of the function based on a range of different values of x between 0 and 4, we will be able to generate a curve with this shape, which predicts with 100% accuracy, because all individuals with prostate cancer will get a value of approximately 1 and will therefore be correctly predicted to have prostate cancer, whereas all the healthy individuals will get a predicted value of approximately 0, which will result in that they are correctly predicted to be healthy. Similarly, the corresponding function of this output node will generate the opposite curve. This is the magical stuff behind neural networks. They can help us to generate nonlinear functions that can fit to almost any data that seems impossible to do with standard statistical methods. We'll now discuss a few similarities and differences between neural networks and standard statistical models, such as the logistic regression model. The input in neural nets is usually called a predictor or explanatory variable in logistic regression. The output in neural nets is usually called the response variable in logistic regression. The weights in neural networks are usually called coefficients or parameters in logistic regression. The intercept in regression corresponds to the bias. We usually say that we train the neural network, whereas the corresponding thing in regression is called that we fit the model to the data, or that we estimate the parameters in the model. The parameters in regression are estimated by minimizing some error function, such as the sum of squares in regression, whereas the corresponding thing is called backpropagation in neural nets, because we randomly assign the weights with some numbers. Then we see how well the network predicts the training data. Then we go back to update the values, so that we improve the prediction. This is iterated until we reach some convergence, where the network can no longer improve the predictions based on the training data. The parameters in regression usually have a meaning that we can interpret, such as the odds ratio in logistic regression, whereas the values of the weights in the neural network usually have no meaning, rather that they're used to make a good prediction. In regression, we usually compute p-values that are associated with the parameters, which require that we fulfill a set of assumptions. Since we use the estimated parameters to interpret the regression model, we must find the global minimum of the error function, whereas this is not crucial in neural networks, because the network might predict the outcome just fine even though it has stopped on a local minimum. Finally, we'll have a look at some basic R code if you like to reproduce the numbers in this video. R is a free software tool that you can download from the following website. We first plug in the data into an R script. We will here use the neural net package, which you first need to install if you have not already done that. Then we load this package and train the neural network, where we try to predict cancer versus healthy, based on the PSA level, which is the only input in this case. We plug in the training data here. Since we in our example like to train a neural network without a hidden layer, we set this argument to 0 and use the logistic activation function. The error function is here set to cross entropy, which in this example is the same thing as using the negative log likelihood function to estimate the weights. We can print the output and plot the network. After 754 iterations to optimize the values of the weights in order to minimize the negative log likelihood function, we have an error of 10.54, which in this case corresponds to the negative log likelihood value. The smaller this value is, the better the model fits the data. For example, if we like to use the network for prediction, we can use the function predict. In this example, the network will predict that the person with a PSA level of 2 is healthy. If you like to compare with the logistic regression model, you can run the following line. If you like to change the error function to the sum of squared errors, you can set this argument to SSE. The reason why I here use a lower threshold for convergence compared to the default value of 0.01 is simply to get similar values as in logistic regression, but this will be more computational expensive. I also recommend that you run a number of repetitions. In this example, we will generate 10 networks that have been based on different initial values of the weights. Then you can study the output of these 10 networks and select the one with the lowest error. In future videos, we'll have a look at networks where the output can result in several categories, compared to the simple binary case we used in this video. We'll also have a look at networks where the output is a continuous variable, and see how the number of hidden nodes affects the output. We will also discuss the problem of overfitting. In another video, I will cover nonlinear regression, which is highly related to neural networks. This was the end of this basic video about artificial neural networks. Thanks for watching.